This question in the probability portion of the Green Book is called Poker Hands. The question says, poker is a card game in which each player gets a hand of 5 cards. There are 52 cards in a deck. Each card has a value and belongs to a suit. There are 13 values, 2 through ace, and 4 suits, spade, club, heart, and diamond. What are the probabilities of getting hands with 4 of a kind, 4 of the 5 cards with the same value, hands with a full house, 3 cards of one value, and 2 cards of another value, and hands with 2 pairs. So like one pair of let's say some number, another pair of a different number, and then the different, like the 5th card being anything else. This question really hits the point of combinatorics, and combinatorics consists of a thing called the choose function. So basically what choose is let's say you have these aces. Let's say the question asks, of these aces, how many ways can you pick 2 cards? Any 2 cards. So like, for example, one of these would be these 2, or these 2, or these 2, or like these 2, something like that. You get, in that value, whatever that value is, I think it's 6. It's 4 times 3 times 2 times 1 over 2 times 2. Because it says the choose function is, it looks like this, 4 choose 2. And it goes the numerator factorial over, not numerator, but like top number minus bottom number factorial times bottom number factorial. So that cancels, and you get a 2 here, so it's 6. Goes these 2, these 2, these 2. That's 3. And then these 2, that's 4. These 2, that's 5. And then I don't know if I counted these 2 already, but that's 6. Either way, you see my point. It's how many ways you can choose two cards from 4. Okay, now for the first question, the first part of the question, it asks about 4 of a kind. So that means we have like 5 cards in like a hand. And we were saying like 4 of them are the same. So they're all like an ace. Like these are like ace, 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 ace. And then it's something else, like 5 or something like that, for example. Well, here's how it goes. The first, like the 4 of a kind part, it can be of a card from any one of these values. It can be all aces, all 2s, all 3s, all 4s, all 5s, all the way up to all kings. So, and there's 13 options. So there's 13 options, and we're saying of these 4, choose all 4 of them. 4, choose 4. And that is 1, because there's only one way you can choose four cards from all 4 cards, and that's just to pick all of them. This represents all the possibilities we can have. We can have 13 different ways of filling up these first 4 cards. So that's the first part of this portion. Now, as for the last part, what possible cards could go in that last slot? So let's say we picked, there's 52 cards total, and we chose 4 already. It happened to be one of the, like some value. It doesn't matter which. We picked some value. How many cards remain in the deck? 48, right? 52 minus 4 equals 48. That means that last card can be any one of the 48. If it was all aces, then the last card can be any of these. If it was the first 4 were kings, all 4 of the kings, then the last card can be any one of these 48. So no matter what the value is we got, we happen to fill in those 4 slots, then the remaining is no matter what will be the other 48. And that's how many combinations you can obtain for number of combinations you can obtain to get 4 of a kind. So 13 times 4 choose 4 times the remaining 48. Right? Because for combinations, you multiply the possibilities. So 48 possibilities, 4 choose 4 possibilities, and 13 possibilities. Why do you do this? For example, if you had you're making an ice cream, and it can be like either vanilla or chocolate, and then it can either be large or small. How many combinations do you have or possibilities? Well, you have 2 times 2 because it can be vanilla, large, vanilla small, chocolate large, and chocolate small. So that's 2 times 2. Same goes for here. You're multiplying up each possibility to get the total number of combinations you can obtain. So that's 4 here. In that case, it's some number we don't have to worry about. You just plug it into calculator. But the question asks for the probabilities. So we have to get some denominator to get a fraction. This is our numerator. Our fraction will be all the ways you can choose 5 cards from 52, right? Because the numerator is that, particularly this way of pulling 5 cards. Now we're trying to see how many ways can you even pull 5 cards, and that's a fraction. Target over total. Target combination is that. Total number of combinations you can obtain is 52, choose 5. Any way you can choose 5 cards from 52. And that's part A's answer. Okay. Now part B. It asks for full house. Hands with a full house. So a full house is saying you have 5 cards. These 3 have some value, and these 2 have some value. Okay? Well, again, we can say the first 3 can have any value, or any value. So 13 possibilities for the values. But now, we no longer choose all 4, right? Because 4 of a kind was all 4, but full house, we have to choose just 3 of them. So it's this part is 4 choose 3. So we've already handled the first 3 cards. We're saying we're trying to choose of one of the 13 values, we choose 3 of them, 3 of the 4 cards available. Then now let's say we took the aces. We've taken we happen to pick these 3. One of the possible ways to choose 3 of 4. Now we can no longer pick this ace, right? So that leaves the other 12 possible values. And so we're trying to get one of the values from the 12. It doesn't matter which. Times 12. And then of that value we're choosing, we're taking 2 of the cards. So it's 4 choose 2. So again, notice it's a little different. Here it says 48, but here we have the choose function twice. That is because in this case, the last card can be any one of the 48. It doesn't matter which. But here we're saying we have to pick one of the values. It doesn't matter which value, one of the 12. And those 12 values each have 4 cards. So whatever value we happen to choose, we'll have 4 options. Of those 4 options, how many ways can we choose 2 of them? And that represents 12 times 4 choose 2. And again, the denominator is how many ways you can choose 5 cards from 52. Okay. Now, next part is a two pair. Two pair says, well, we have 5 cards again. We're saying these 2 cards are the same. These 2 are the same, and this one is different. So these are some value. These are a different some value, and then this is a different value. So we're dealing with 3 different values for 5 cards. So in this part of the question, so we have 13 values, right? And 2 of them are the same. So we need to pick 2 values. We're trying to choose 2 values now. How many ways can we choose 2 values? Before it was just saying, oh, 13, right? Because we're just saying of the 13, this really is just saying of the 13 values, choose 1. And then we're saying for this one, of the 13 values, choose 1. Again, here now, of the 12 values that remain, choose 1. But instead, here we're saying, of the 13 values, how many ways can we choose 2? So we have to write 13, choose 2. How many ways we're able to choose 2 cards? 2 values, sorry. Okay. And then this next part is, well, for the first one, for this batch, we have 4 options. And of those 4, we choose 2 of them. 4, choose 2. But then again, we have, for this batch, we also have 4 options. And then we again choose 2. Now for the last card, we can't just say 48, because even though we've chosen 4 cards total, we can't subtract by 4, the total number of 52 by 4, because let's say we happen to choose, let me erase all this. Let's say we chose these aces and these 7s. For 13, choose 2, we chose ace and 7 as the values. And then for ace, we could choose 2. There's 2 ways to choose an ace of the 4 options. And then for the 7, there's 2 ways to choose 4 cards of 7. Now, if we said the last number be 48 for all possible other cards, well, that would include, let me get this, that would include obviously other cards that we have left, but also it would include the ace, the other aces, and the other 7s. Now, if we happened, by chance, to get one of these aces, that would make our hand turn into a full house. Because now we have 3 of the same value, right? And then 2 different. So we can't allow this ace or this 7 to be picked at all. So actually, instead of saying times 48, what we really have to say is, well, we also can't include these two, or these 2. So actually it's times 44 possibilities all over 52, choose 5. Okay, so these are the answers. Okay, I want to also clarify an extra point in this. As you can see, for a 2 pair, we have the 13 choose 2 element. We're saying we're choosing 2 cards of the 13. But for a full house, we still kind of have 2 card options. We still have 2 choices. That's because the choose function does not care about order. As you can see, for example, if we chose this one, then this one, or this one, then this one, it still has the same, it counts as one pick. Because that's how you can choose it. It's not about the orderings of the choosings themselves. So in this case, for the two pair, we're saying, well, if we don't want to count Jack, Jack, Ace, Ace, 2, and Ace, Ace, Jack, Jack, 2 as different hands, because it's the exact same hand with different ordering. But for this case, we do want to differentiate Jack, 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 Ace, Ace with Ace, 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 Jack, Jack. So just to clarify, the choose function neglects order. So, and that's what we want in this case, because we don't care about the order of the ace and the jack. It's about the value of the hand itself. So 13 choose 2 says the orderings in which you get the two values does not matter. But in this case, we're saying actually it does matter, because if we have a hand with 3 jacks and 2 aces, as opposed to 3 aces and 2 jacks, those actually have different values in poker. So I wanted to clarify that differentiating factor between full house and two pair. And yeah, that's the final answer for these questions.